So this is the so in this example problem, what we'll be looking at is we'll be looking at the uh, we'll be looking to determine the zero force members that are that are present in this truss for the given loading. All right. So even though there's gusset plates used here, we're treating all the joints as being connected at pins. All right. All right. So when you have these types of problems, these truss problems, what you should first try to do, all right, is try to identify if there's any joints in the structure that have three members going into them. So should be three members going in to the joint. All right, and then if two of those members are acting along the same direction, that is a good candidate for a zero force where a zero force member would be going along. All right, that would be a joint to pick. All right, so in this case here, all right, we have a couple of locations that would fit that bill. We have joint D. All right, it has two members that go along the same direction. We have the joint CD, or we have the member CD, and we have the member DE that both go along the same direction. And then we have one member DF that goes opposite or is at 90 degrees from that. And then we also have joint G here. We have HG, members HG and GF go along the same direction, and we have member GC is 90 degrees opposite of those directions. All right. We also have joint B that has a similar situation where we have AB, all right, and we have BC that go along the same direction, and we have BH that goes whatchamacallit, that goes opposite or is 90 degrees apart from AB and BC. All right. So we're just going to do the free body diagram of these joints one at a time, and we'll see whether or not there are any zero force members there. All right. So we'll first do at point D. All right. So at point D, we'll have a force FDC. We'll have another force that goes along member DE, FDE. All right, and then we have a force that's 90 degrees from those. We'll call that FDF. All right. So if we set our XY coordinate system where the x-axis goes along member DE or member CD, and we sum all of our forces along the y direction, the only way this would be true would be if FDF would be equal to 0. All right. So we can get rid of FDF from our analysis because it has no force there. All right. So what we can now do is we can actually take a look at joint F as well. So let's look at the free body diagram at F. All right. So since we will have at F we have two members GF and FE that go along the x-axis. So I'll say FGF, then FFE. All right, we'll go along the x-axis, and then we'll have a force that goes from point F to point C, which we'll call FFC. All right, and then we did have a member that went from point F to point D, but we know that FD is equal to 0. All right, so we can say, so if we again use our equilibrium equations, and we sum all the forces in the y direction, all right, we know that FGF and FE will have no y component, so the only component would be the y component along FFC. So what we can say is that FFCY must be equal to 0. Therefore, FCX would also have to be 0. FFCX would have to be equal to 0. Therefore, the total force that goes along member FC would also have to be equal to 0. All right? So we can say that this member here from point C to point F would also have no force in it. All right? So what we can now do is we can look at, we need to draw the free body diagram at point G. So at point G we have FGF, we have FHG, and we have FGC. Alright, so again, you can define our xy coordinate system with our x-axis going along GF or HG and our y-axis going along the member GC. So if we sum our x forces in our y direction and set it equal to 0, you would get FGC, alright, as being our only force. So therefore FGC is equal to 0, and we can eliminate that member from our analysis as well. Right. So we're left with the last free body diagram we're going to draw is of the joint at point B. So if we look at point B, we have the force that goes from point B to point A. We have the force that goes from point B to point C. All right. We have the force that goes from point B to point H. All right. And then we also have an external load of 2 kilonewtons. All right. So if we define our x and y coordinate where x goes along the BA or the BC axis, and the y goes along the BH axis, what we'll get is that if we sum all the forces in the x direction and set them equal to 0, we'll get FBC minus FBA must be equal to 0. So we know that the magnitude of FBC and FBA would have to be equal. Alright, when we sum all the forces in the y direction and set them equal to 0, because we have a negative 2 kilonewton external force, we know that FBH will not be equal to 0. In this case, FBH would be equal to minus 2 kilonewtons, which means that it is in compression. Right? Or it would be going into the joint. Alright, so in short, we can redraw our original truss. It becomes a heck of a lot simpler because we eliminated a lot of our free body diagram. So we'll have our pin at point A. Alright, we will have our members. We'll have our joint at B where we have our 2 kilonewton force here. Alright. Alright, we have our point H where that short joint that we just connected meets up with member B, BH, and then we'll have another force here, member here, another member here, and then we'll have another member here, and we'll have a last member here. all right, where we have a rocker at point E, and we have another 5 kilonewton force that's applied at point C. All right. So by using this analysis, it's really we were able to reduce our truss from, let's go to the top here. Able to reduce our truss from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 members down to 1, 2, 3, 4, 5, 6, 7 members. All right, so we reduced our calculations in half, essentially. All right. So that concludes this example on the benefits of identifying the zero force members initially to make your calculations, your method of joints calculations a lot simpler.